Hi, welcome to this video. My name is Phil and I am a Senior Lecturer in Astrophysics at the University of Lincoln. I'm also the Programme Leader for the Physics with Astrophysics programme that we do here, and as a result of that we have lots of interesting astrophysics modules which you can do if you're doing the physics degree as well. But if you're in the Physics with Astrophysics, then these are basically going to be core modules. Now what I'm going to do with this particular video is give you a sample of one of our third year astrophysics modules that you would do here on this particular program. So this particular module is going to be called Galactic and Extragalactic Astronomy. It's in your third year. It's going to be a core module if you're doing the physics of astrophysics. And the aim of it really is to understand galaxies and kind of the larger scale structures that they then form in the universe. And we save the other large scale stuff for cosmology, but we touch on galaxies here. So how we can understand galaxies from observations, and from those observations come up with theories of how they might evolve and how they evolve through time, and what they might end up being. So this is the whole aim of the module. And what I'm going to do here is just give you a sample one from somewhere in between that particular module. So we may actually have around 30 lectures in the module. We'll have about 10 to 12 practical sessions, so one every week, where we work through some example problems relating to the lectures. And then we have about 3 or so lectures a week. So this one is going to be lecture 4. This actually just gives a complete overview of galaxies before we get started. And the reason why we do this early on is that we learn what spiral galaxies are, elliptical galaxies, all the different sorts, and some general properties of them. And then what we do is we go back to those in later lectures and we look at them in more detail. So we specifically focus on spiral galaxies in lots of detail. What sort of observations can we make? That sort of thing. Now before lecture 4, so lecture 2 and 3, because actually lecture 1 is normally an intro lecture where we just set out what we're going to be doing on the module, we would have actually put galaxies in the context of the entire universe before we then look at galaxies. So this one's going to be galaxies. Now, what we're actually doing here, now if you're actually on the course itself, when you get to third year, you'd have had a year gap between doing your introduction to modern astronomy in your first year, which I also have a sample lecture on as well. Now, one of those lectures that we do, or part of the actual topic of that introductory module we do in the first year, is galaxies. So this particular module, or this module with this lecture here, is going to recap a lot of the stuff that we would have gone over for that, while setting ourselves up for doing the more detailed lectures later on individual ones. So the whole point of this is to point out all the different sorts of galaxies that they have. They have an enormous range of different sorts, types, things like that, and we're going to touch on those. So we're going to do more in detail as we go through the actual course in the module. So just to recap what a galaxy is, it's been a long time, maybe you've forgotten. So galaxies are kind of large structures. They're comprised of stars, dust, gas, dark matter, and they can range in size from 1,000 to hundreds of thousands of parsec in diameter, so they can be quite small. The smallest ones are going to be known as dwarf galaxies. The biggest ones can be like giant elliptical galaxies. These are enormous, and anywhere in between basically. And they're typically going to be separated by 1 million parsecs or something like that, approximately, because that's not always the case. Some are actually colliding. You've got some galaxies here that are actually satellite galaxies of other ones, so they're closer. They're smaller dwarf galaxies orbiting around the outside. Anyway, so this particular one here is the Andromeda Galaxy, and it's our closest galaxy. Now I've put closest, it's our closest significant large spiral galaxy. There are other smaller ones, so you can see at the bottom there are a smaller dwarf galaxy there. The Milky Way has its own dwarf galaxies, but this one here is about comparable sort of size to the Milky Way. It's just over 100,000 light years across. It's our closest one. And most galaxies contain anywhere from 10 to the 8 to 10 to the 14 stars. And now if you think that there's about 10 to the 12 galaxies in the known observable universe, you can start to get an idea of just how many stars there are that we know about. They're just the ones that are in our observable universe, not the ones that we can't see. And again, just to give you an idea of how many galaxies there are out in the universe, approximately 1/1000th of all the grains of sand on Earth represents the stars in one galaxy. So that gives you an idea, really, of just how many stars there are just in one galaxy. And then when you consider how many galaxies there are, well, this is the Hubble Ultra Deep Field image. It's about 3 arc minutes across, and it contains 10,000 galaxies in. So each one of those objects in that picture there is a galaxy. And you can see straight away there's a whole range of different sizes, colours, shapes, because there is just an enormous amount of them, different sorts. If you don't know what 3 arc minutes is in the sky, this can give you a bit of an idea. So next time you look out into the sky and you see the full moon, the Hubble Ultra Deep Field is just a fraction of the size of the full moon in the actual sky itself. So you look out, the full moon doesn't fill the sky. It's actually relatively small when you consider the whole sky. You've got the planets, and this small section of the sky that Hubble looked at for a long period of time has got 10,000 galaxies in. So if you then extrapolate out to the entire sky, you can start to see just how many galaxies we actually have. So, an idea there. About 2 trillion galaxies in the observable universe. Again, that's what we can see, or in the observable part of the universe. So most galaxies have a supermassive black hole in their centre, which can be on the order of billion solar masses. Again, as we learn more about galaxies, this isn't necessarily going to be the case. They can have a range of different sizes, and they don't all have these supermassive black holes at the centre, but a good majority do. The galaxies themselves are gravitationally bound together. Some of them rotate, some of them don't. Again, we're going to touch back on which ones do and which don't. These two here are spiral galaxies, so they actually are disk-like galaxies. They're also star-forming galaxies, so they're forming stars. But most are gravitationally bound with those black holes in. Now, we're inside the Milky Way. Our galaxy is called the Milky Way, and we don't have an image of that because we're inside it. It's pretty hard to take a picture of it. So just imagine sitting in your car or even in your house, and you can't leave it, but you need to get a picture of the outside of it. It's pretty hard to do. So you can only really see from inside out, and this is what we see being inside the Milky Way. We get this band of stars across the sky if you've got good seeing conditions, and that represents the main disk of the disk-like spiral galaxy that we reside in. Now, we're approximately here. The Milky Way is a barred spiral galaxy, and it could be a 2 or a 4-arm galaxy. We don't actually know. And there's lots of arguments currently about how many arms the spirals, or how many spiral arms there are, if it's 2, if it's 4. It could actually have 2 and 4, so it could have 2 close into the centre and it could have 4 further out, and it kind of splits. And where we are located and things like that, there's a lot of uncertainty because we're inside it and it's pretty hard to see and figure out. But we can look at other galaxies. And that's how we've learnt about the Milky Way, by looking at other galaxies and similar types. So, main types of galaxies then. The top 3 are typically star forming, although you do get star formation in all of them. You can do, but the rates of star formation are significantly less. So barred spirals and spirals are pretty much the same thing. The only significant difference is they have a bar in the centre. Irregular galaxies don't have any uniform shape, but they do have significant star formation occurring. You've then basically got your elliptical galaxy and lenticulars. They have much older stars with little to no star formation because they don't have any gas in them anymore, so they don't have a lot of ongoing star formation, and because of that, their stars are old. The ones along the top are going to have newer stars, younger stars. The peculiar and the irregular galaxies just have unusual shapes. Peculiar galaxies are kind of shaped most often by internal processes that give their unusual shape. They could have an active black hole, they could have powerful jets coming out, things like that. But again, we're going to come back to these and look in more detail to explain why they look like that, why they've got star formation, why they haven't got star formation. Now, if you're going to be learning about galaxies, this is something you're going to keep coming back to a lot of time. So this is, well, it's kind of known as the tuning fork diagram. It has a few different varieties. Sometimes it has this intermediate spirals in the centre part on the right, sometimes it doesn't. but either way, it's kind of set out a bit like a tuning fork. And it's got your ellipticals on the left, it's got spirals, barred and intermediate ones, and then irregulars and things like that. And looking at that, you would probably expect or think that the evolution of a galaxy would go from left to right, but it's not. It's down to historically how they were originally observed and labelled, but it's actually the other way around. So they actually go from the right-hand side to the left-hand side. So they go from spiral galaxies to elliptical, and then the lenticulars are kind of in the middle. Now what we actually have here in the green section there, these are known as late stage, and again this is historically down to how they were labelled or things like that, but they're not really old. It's the other way around. They're actually younger, but they're known as late stage. Then on the other side, your early stage ones, noted as the blue, these are older. So they're called early stage, but they're actually older. You've then got your later stage, which are younger. They're your spiral, star-forming galaxies. And then kind of off to the side on their own, you've got these extreme late stage dwarf galaxies, irregulars. So these could be like precursors to spirals. They're in the process of forming into spiral galaxies. They're just dwarf galaxies. Or they're irregular galaxies that don't really fit a standard sort of shape. So they kind of sit there off on the right. And they quite often can then go, or that pathwise track, they can track onto the late stage, because that is why they're kind of known as extreme late stage galaxies. So you're going to come back to this pretty much every lecture, I would imagine. It's a very useful diagram. So what we're going to do now is we're going to touch on a few of these different sorts of galaxies and just give a basic overview of them. So when we do our main lectures later on, we've got a good understanding of what to expect, I suppose. So spiral galaxies, visually, the most obvious thing here is they have spiral arms. And these can be quite clear to see. Now, again, when we look at spiral galaxies in more detail, we get different sorts of spirals. So we can get grand design spirals, we can get flocculent galaxies. This basically means that they have a complete spiral arm, or it's more patchy and broken. So there can be different degrees of completeness. They also have a central bulge, so like a spherical dense region in the center around a supermassive black hole. And your star formation typically occurs in the spiral arms. You have these hydrogen clouds, which are, so you've got your ionized hydrogen there, which is the red parts. You've then got bright blue stars, which have just formed there. So spiral galaxies have star formation predominantly in the spiral arms and the disk part of the galaxy. Now those spiral arms are due to density waves, and they co-move with the actual movement of the stars. They're not static. So the spiral galaxies are kind of rotating. The spiral arms are also rotating, but at a different speed to the stars. You can imagine it's a bit like traffic down a road. If someone brakes in front of you, then everyone does the same thing, and then there's a density wave that passes back through the traffic. The density wave moves kind of independent to the stars or the traffic themselves, and this is known as a certain type of resonance. Anyway, we'll do more of that later on. So going back to the diagram again, because we have different sorts of spirals here. Now, as you go from the left to the right, so these spiral arms become more open. And I should say, if I switch the arrow the other way around, as they evolve and get older, their spiral arms get tighter, they get more wound up. They then actually increase their size of their bulge as well. So the central bulge part gets larger as they evolve. They also deplete their gas. So as they evolve towards the elliptical side, they lose their gas because it gets turned into stars. Not turned into, but it forms into stars basically, and then there's less of it left. So increase in hydrogen gas as we go towards the right hand side. So some general rules for spiral galaxies, or I say rules or just some properties in general. This is a side view schematic of a fairly typical spiral galaxy, a bit like the Milky Way. Now you have this central bulge. The central bulge is quite red because it's populated by old red stars. It's quite densely packed. There's not really any gas or dust there. Now again, there are different sorts of bulges you can have, and this is a very big generalization. You can get gas in them and things like that. If you have a bar, they typically draw in gas. But anyway, that's a topic for other lectures. Generally, there's no star formation occurring in here, but then we have this disk, denoted by the green arrow here. This is where you're going to get your younger stars. So the star formation mostly occurs in this disk component. This is where the gas is. So you have your young blue hot type O and B stars. So if you've learnt about stars, you will know what the type O and B are. They're your biggest, brightest stars. They don't live for very long, which is why they're young. And they occur in this disk part. Now we also have a halo. There's like a fairly low density halo around the galaxy itself. It's spherical, and this is populated again by very old population 2 stars, red stars, and they clump together to form globular clusters, and they're quite sparsely separated. So they're almost like dwarf galaxies that are orbiting around the outside of the main galaxy. There's no gas or dust here, so there's no recent star formation. So that's why they're quite old. You don't really see any blue stars. However, you do see blue stars, and they're known as blue stragglers. Again, we're going to touch on that a bit later, but you can get younger stars there, but it's because they're colliding, because they're so densely packed. So, your blue straggler stars, because they're so densely packed in these clusters, we can get collisions between two old stars. Now, because the vast majority of a star is hydrogen, even when it comes to the end of its life, when you merge two together, you can form a new star, but it has a combined mass that's greater, essentially. So you get a bigger star. Bigger star means it's going to have a hotter temperature. It's going to be bluer. So these blue straggler stars can form in the globular clusters. Now, if we were to look at the HR diagram of one of these globular clusters, we'd get something a little bit like this on the right-hand side. And if you haven't seen the HR diagram, then I've done a sample lecture for part of the introduction to modern astronomy, which you can check out. If not, go back and recheck for your actual for this particular module. But anyway, what we have here, we have the stars plotted for luminosity against temperature, and we have the main sequence, which is that diagonal part. Hotter stars sit towards the upper left, cooler stars lower right. And in a globular cluster, we would expect there to be a significant amount of your older red stars, which is highlighted here. However, there's actually these blue stragglers sitting there, which shouldn't really be there due to the age of the clusters, but they are there nonetheless. So, star formation then in your spiral galaxies. It typically occurs in these H2 regions, these ionized hydrogen regions. And these are gas clouds that are then ionized by the young hot stars that have then formed. So they're then emitting at their own wavelength. This is the Orion Nebula, which is a fantastic object if you get to actually see this with your own telescope. You'll only see the colour if you put a camera on. But nonetheless, you'll still see some of the structure. You should still pick out some of the blue stars. Those blue stars have just formed in that nebula, basically. And if you were to measure the spectrum of light coming from that nebula, you would be able to pick out specifically hydrogen, which gives you the kind of reddish purplish colour. You've got oxygen, you've also got nitrogen, and a few other things there as well. So it's emitting at very narrow wavelengths there, basically. So with spiral galaxies, we have the late stage ones and the early stage ones. Now, the SAA ones, these are normal spirals, which are late stage spirals. So we get that right the right way around. So these are, no, they're not late stage, sorry, it's just the other way around, isn't it? So these are older stars in here. So that means the galaxies are older, so they're early stage. It's always confusing having it that way around. Now these ones, again, have a large central bulge, old red stars in the centre. They may have a black hole up to 10 to the 9 solar masses, and they can have large dust lanes like this one here, so the Sombrero Galaxy, or Messier 104. they don't really have the star formation regions because they've depleted all their gas, because these are at the later stage of their evolution now. So they don't really have much active star formation occurring. And these are some other images of the same classification of galaxy. You'll note these appear, or they should appear, a little bit redder than a younger one. So you've got your spiral arms are quite tightly wound. There's no bright red and blue regions to denote there's actually any star formation occurring there. There will be star formation, but it will be quite weak and very low rates. Now, if we go to the younger ones, these are your late stage ones. Again, hopefully got that the right way around. These have got a smaller central bulge with a supermassive black hole. You can see in the visible and the infrared, you can see that actually there is star formation occurring. There's large amounts of hydrogen there, and it can also extend well beyond the galaxy itself and undergo star formation. This one here is the pinhole galaxy, and in the spiral arms you can see there's quite intense regions of star formation. That's where this hydrogen gas is collapsing as it goes into the spiral arms. You get a sudden burst of star formation occurring, and in very young galaxies, spiral galaxies, this star formation can be so rapid that they can be known as a starburst galaxy. Also, some irregular galaxies can also be known as starburst galaxies as well. So some images then of these late stage or younger spirals. Again, these are going to look bluer than an equivalent or same sort of size older one or early stage spiral galaxy. And you can see in the spiral arms you've got those bright kind of pinky red areas with lots of blue stars in them, confined mostly to the spiral arms. So this is a key feature really with these sorts of galaxies. Now, what we can do with spiral galaxies specifically, because elliptical galaxies don't really have hydrogen in them anymore, is we can map out the hydrogen abundance. So we can look at the neutral hydrogen line. So it is the 21 centimeter emission line, and it's in the radio part of the spectrum. So we can map out where this hydrogen is. This is kind of cool regions. And this is likely where we're going to find star formation as well. So this is going to be where we've got these clouds of hydrogen gas, which are then going to collapse into stars. And here, when we can actually do this, we can also use the Doppler shifting of that line to get the rotation. And rotations of spiral galaxies is quite an interesting topic, really, because it's essentially where dark matter came from, because they don't rotate as they should. Now, we can use other tracers to get the things like the rotation and the mapping out of star formation. So other reliable spiral tracers that they will actually use to map out things like the spiral arms will be giant molecular clouds, the 6.7 gigahertz methanol maser. You've got your ionized hydrogen regions. All of these spatially relate to high mass star formation, and it mostly occurs in the spiral arms. So if you can map out where the ionized hydrogen is, the giant molecular clouds, the masers, that can then also give you the same sort of mapping out for your spiral arms. And we're going to look at this in a lot more detail when we look at spiral galaxies specifically, but in our own Milky Way, we're able to get the width of the spiral arms and specifically the structure, because there's actually an interesting offset as well. Like the gas component of a spiral arm is slightly offset from the star formation. So the gases kind of might appear first, they collapse, form stars, and the stars occur. So as you go through the spiral arm, you get slightly different things. But we're going to look at that in our lecture on spiral galaxies instead. Now, barred spiral galaxies and also actually intermediate spirals are the same as spirals. They just have a different central feature. So all the other properties mostly are fairly similar. Now, 2/3 of all spiral galaxies show a bar at their center. And this can actually act as a funnel, and it can drive material into the center part, and that can then actually feed a black hole. So we've got those supermassive black holes in the center. That would then become an active galactic nuclei. We call those AGNs. And that's when we get these really powerful quasars and blazars and things like that, when we're actually feeding these black holes. Now, we are a barred spiral galaxy, the Milky Way. At the moment, it's not active, but it has the potential to feed significant amount of gas into the centre. So these are, same as the normal spirals. Intermediates just sit somewhere in the middle, and they're likely a transition between one and the other. And why do I say it's a transition? Well, we believe that barred spiral galaxies are somewhat of an evolutionary point of most spiral galaxies. So if we look at high redshift galaxies, that's galaxies that are much further away, and that would be galaxies which are in the earlier part of the universe, because actually when you look at long distances in the universe, that corresponds to time. So if you look back in time, only 20% have bars. But if we look at current galaxies in our local area, 70% have got bars. So it could suggest actually that it's an evolutionary phase of a spiral galaxy to form a bar. We still don't know a huge amount of them, but still. So going back to the rotation curves, once we can calculate those rotation curves by mapping out like the Doppler shift in the galaxy, we find that they're kind of flat. Now, they shouldn't be. If we use normal Keplerian laws, the further away that a star is from the centre of the galaxy, it should orbit slower. But these rotation curves here are flat, which means they're rotating too fast in the outer part. Now, the only way that can really occur, or one of the best explanations, is that we have these dark matter halos. We have more mass around the outside of the galaxy, which can act to speed up the rotation of the outer part of the galaxy and give us these flat rotation curves. Now on to elliptical galaxies. Again, we're going to do a full lecture on these, but these are fairly featureless, and some general rules really for elliptical galaxies. They don't have spiral arms, they are ellipsoid, or they're spherical in shape. They can actually be anywhere from perfectly spherical to almost cigar shaped. Now, when I do the lecture on ellipticals, I'm going to address the E7 side. I think it's like E5 to E7. The elliptical parts, it's quite possible that these are not actually genuine elliptical galaxies. They could be things like edge-on lenticulars. But again, we'll figure out why that's the case in our lectures as we go through. These particular galaxies don't really have any gas or dust for star formation. They will have small amounts, and they will have small amounts of star formation, but it will be an order of magnitude less than for an equivalent spiral galaxy. Because of that, their stars are aging, they're old, so they will appear quite red in comparison to spiral galaxies because they've got these old red stars in, no recent star formation. And then you've also got two main types. You've kind of got boxy giant ellipticals. It means that actually they've kind of got more square corners on them. Disky ones are kind of more disky, I suppose. They've got asymmetric random motions. What that means is the motions of the stars are more random. They don't really have a net rotation. Now they can, but they have more velocity dispersion than a spiral galaxy in relation to their rotation. So they're more the motions are more randomized of the stars. So just to give you an idea of what the boxy and the disky ellipticals look like, it's just deviations away from these particular contours, which is a contour of the same surface brightness, and it can be more box-like and it can be more disc-like, but we're not too worried about this at the moment. So some key features then between spirals and elliptical: because they are dominated by more older stars, they don't have any emission line due to star formation. Then the spectrum of all the different sorts of galaxies look different. Now the top two there, the first one on the upper left is an E4 elliptical galaxy. It doesn't have any emission lines from those ionized gas regions, I suppose. There's no star formation. They've got old red stars. The whole spectrum is over towards the red part. And then on the other one, you've got an SA. That's a early stage spiral, so an old spiral. Almost the same features, except it does have a very weak hydrogen line because it's still undergoing a small amount of star formation. Again, very little ionized gas there. Now, the bottom two are young spirals, an irregular galaxy or a starburst galaxy. These have a significant amount of ionized gas. You can see by those vertical emission lines representing the star formation. You've then also got the overall spectrum is towards the blue part, so towards 4,000 angstroms or 400 nanometers. It's peaking towards the blue. We know that because there's more blue stars there. The other ones are the other way. You also have this step or this break at 400 nanometers. You've got old red stars. There's a lot of metallic lines in the same sort of area that overlap from all the different stars, and then you get a sudden kind of discontinuity at 400 nanometers, and that's very typical of galaxies that have old populations of stars. So just to kind of point that out really, top one elliptical, no emission lines. You've got strong absorption lines from metals present in the atmosphere of old stars. You have a very strong 400 nanometer break, so you have this vertical kind of step because you've got those old red stars and all of those metallic lines overlaying. Spiral galaxies, they do have emission lines, they have active star formation. They've also got absorption lines from a population of younger and older stars. They have, depends on if it's a late stage or early stage, but they can have a weak or non-existent 400 nanometer break, depending how many old stars are there. Irregular and starburst, these have very strong emission lines. They have significant amount of star formation occurring. Very, very weak 400 nanometer break because they have very little red stars there, or if they do, they are overpowered by the much brighter young stars from the star formation. So just comparing ellipticals to spirals, colour-wise, we would expect elliptical galaxies to be redder because they have much redder stars as a population than your spirals, which appear bluer. So always remember, spirals blue, ellipticals red. Size difference as well. Elliptical galaxies, they typically have a very large range of sizes, but they can get exceptionally large. So these can be typically larger than spiral galaxies. This is just to give you an idea of the sort of sizes compared to the Milky Way, the Andromeda, and some other galaxies as well. So these can get quite large. So you're talking millions of light years across now, very big galaxies. So what we're going to do now is just quickly finish on irregulars and things like that, and then we'll essentially finish our lecture, and we're set up for then looking at these galaxies in more detail with separate lectures themselves. So elliptical galaxies, they can form from mergers of other spirals or smaller elliptical galaxies, and in the process of that you then get these starburst galaxies or irregular galaxies. As they are merging, they have irregular shapes. They don't have a set shape, so they're just known as irregular. But because they have gas in it, if it's a spiral galaxy, that will drive massive amounts of star formation, which collapses the gas, and they can be called starburst galaxies. Now, as we mentioned before, if you look at the spectrum of one, then we get very strong emission lines, and this is down to, the large amounts of ionized gas that's formed or comes about due to the star formation process. They appear very blue because they have a lot of these really massive young hot type O and B stars, which are blue. So we see the whole spectrum from the galaxy appear blue. Now, peculiar galaxies are kind of similar to irregular, but these also include galaxies that have got active galactic nuclei, or they have an unusual appearance due to an internal process. Again, they're probably shaped by their black hole. Now, this is Centaurus A. It's a large elliptical galaxy. It merged with a smaller spiral galaxy a few 100 million years ago. Now, what's happened there is the supermassive black hole in the centre, or it's been fed, all that material from the merging galaxy got fed into the black hole, it's become active, and it's created these enormous, energetic, perpendicular radio jets. And this would be known as a peculiar galaxy because it's shaped by an internal process and it's got an active galactic nuclei. We've then got lenticular galaxies, and lenticular galaxies kind of sit in between elliptical and spiral. So a spiral galaxy can kind of evolve to elliptical, then not elliptical, yeah, to lenticular and then elliptical. Now they share properties with both spirals and elliptical. Like elliptical galaxies, they have old red stars. They have very little gas, very little star formation occurring, but they are still a disk galaxy. So they still have disk-like dynamics. If they're edge on, it's very difficult to distinguish if it's a lenticular or an elliptical. And actually, when we look at lenticular and elliptical galaxies later on, we're going to find out that actually quite a lot of elliptical galaxies have been misclassified, and they should actually be lenticulars because it's very difficult when they're edge on. They appear like cigar shaped, which is like your E7 elliptical galaxy. So thank you for watching, and if you enjoy this, then do check out some of the other sample lectures, but thank you for watching.